Okay, Bismillah ar-Rahman ar-Rahim. Dear students, today we talk about synchronization. Inter-process communication, we did it in the last video intro of that. Now let us talk about the synchronization specifically in this video, right? So before talking more technical, let me give you an analogy, an example. Say for example, you got a one washroom. Okay, so you got a washroom and you got three brothers, brother 1, brother 2, and brother 3. Okay, and they want to actually bath. So when they are bathing, say for example brother 1 goes into the washroom and he starts bathing. Okay, and he's putting on the water on the head, some soap on his head, and he's not yet finished. He's just started bathing. Okay, he has put up the soap on his head and his face, for example, and 2 comes in. Brother 2 comes in and he sees that brother 1 is there. So now your scheduler, like an operating system, can preempt, because maybe its time slice is over, you can preempt it and the second one goes in. But the thing is, bathing is a kind of thing which can't be preempted, right? You have to use the resource. Say for example you are using a resource washroom, you have to use it for entirety. You have to do it, this job is to be done fully. Okay, if not, if you are preempting it, now the 2 goes in and the 1 comes up. Say now, say for example this is the 1 and 2 is inside, and he has some soap on his head, okay, on his eyes maybe, and now the 3 comes in, and maybe the 3 goes in and 2 is preempted. So 1 and 2 is here, 3 is inside washing something, and say they have washed their heads only. Now what will happen is their soap will go into their eyes and they're gonna bump each other's head, okay, and break their head literally. So what I'm talking about is that this resource can't be preempted. Okay, so for example I gave the last time example of the printer. Now these are 3 processes. Now one process is process 1, process 2, process 3. You can't write a line of the P1 and the line of the P2 and a word of the P3. You have to write it in as a whole, one document from the P1, then you can do to the P2 and so on. Okay, so that means what we do is, like we do, say for example brother 1 goes into the washroom. Okay, when the brother 2 comes in, he does what? He doesn't go, he's not allowed to go in because the door is locked. So we got a lock. That is important, right? You have to lock the washroom before you actually bath, literally, because you're naked and you can't actually leave it. Okay, so you can't leave it for the brother 2, so you got to lock it. Now what will brother 2 see? So this is 2nd, this is the 3rd one, and this is the 1. 1 is bathing. What will the brother 2 see? He will see a lock, so he will desist. He will not go in. He will wait. So that's important. He is gonna wait, right? Now and same is true with the brother 3rd. Now how you gonna wait is a question. Now will you wait, say like this, that you are checking constantly, hey, is this door open, is this door open, is this door open, and he sees no, brother, it's locked. So he stays there, and he goes again, he goes again. So he's kind of a loop, he's in a kind of a loop, and this thing is called as spin lock. So he's spinning, he's looping in a chucking, trying to see is the door open or not, open or not, open or not, right? And one time will come when brother 1 will finish, he will release the lock, and this guy can access the washroom. Okay, so this is the one way. In a computer analogy, for example, we got, say, a printer, and say P1 is printing, so P2 want to print, but it sees the P1 has locked, so we got to lock the printer. So P1 has locked the printer, P2 is gonna chuck in a spin loop. Is it free, is it free, is it free? What will happen by that is there will be a lot of CPU cycles wasted, because it's the CPU who is gonna do this thing. So that means the CPU cycle is wasted in this busy wait. We also call it as a busy wait, okay, or spin lock. So you are spinning and trying to see, Okay, that's not a good idea. You can do other things. Say for example, I say for example, brother to knock at the door. He said, hey, it's occupied. Now what he do is he go and do some other job, and it is the brother one who come back and tell brother two, hey, it's free, you can go. Okay, so that means another process one here finishes the printer job. It is the responsibility of the process one who has locked a resource to tell other guys who are waiting. They may be waiting in a queue, but that may be sleeping queue. We'll talk to them later on when we talk semaphores and all. So they may be sleeping in a queue. Okay, and it is the process one who has a responsibility to wake some process. Say P2 and P3 will be now here to tell them, hey, the resource is free, you can go ahead, right? Now this resource which we talked about uh, is called the critical resource. The important thing is that if say for example there are some processes P1, P2, P3, they are, say this is accessing the printer, this is accessing the disk, this is accessing something else, then they don't need a synchronization. Synchronization is needed if they are accessing something. Say for example, if they are accessing a file and both of them want to read, now there is no problem, you can read, both of them can read, no problem at all. So the problem occurs, the synchronization problem occurs when you are accessing a particular resource and that resource is non-preemptible. You can't preempt it. Okay, that means a job like an example I said, a washroom, or here, or a printer. That printer is a non-preemptible resource. Okay, that thing is called as a critical resource. And the code which accesses that, like a print command, is called as a critical section. Okay, now if I give another example here, say for example you got a variable, say for example count. This is a shared variable, and in a multiprocessing system or multitasking system, you know, multiple threads, multiple processes try to access this. Okay, say for example some process one is trying to make it plus plus to the count, and other guy is P2 is making count minus minus. Okay, so what will happen is it will mess up if we don't give a synchronization here. Like I gave the example of the ADM and the cashier system in the previous video, right? So it can easily mess up, you can think of it. So you need, if the two processes are accessing a shared resource simultaneously and are doing some mess up with it, this thing will be called as a race condition. So this is a race condition now, and we need to do some kind of synchronization, and that synchronization is actually called the serialization as well, or you can say simply a synchronization. Okay, now you can serialize. There are two ways we can do it. One is simply because who is the guy which schedules the processes P1, P2 or P3. Say there is a part of OS which preempts P1 and loads P2 and preempts P2 and loads P3 and so on in a round robin fashion, whatever scheduling algorithm we have. That is a scheduler. So we can put off the scheduler. This is the first thing. You can say, hey, come on, scheduler, if P1 is accessing, say, this printer or some shared variable or whatever, I put off scheduler to the sleep. That means I'm not gonna, that when the scheduler is off, then P2 or P3, there's no chance to come. And you can say, anyways, they have to wait. So if you put a scheduler off, they have to wait that way and this way also, but they will not mess up, they will not lead us to the race condition this way. So it is gonna be good, right? But it's like our Indian PM. I'll get an example that he wanna kill, say for example, the demonetization he did in India, that in a pond there are 2 crocodiles or 3 crocodiles. But what you are doing is you are trying to kill, bomb or poison this pond because you want to kill these crocodiles, but there are a lot of fishes, okay, flora and fauna that will also get killed. this is the same like this, that I'm saying there is a contention because between these three processes, for example for a printer or this here resource here count. But when I put off the scheduler, what about the other processes? They will also get hampered. So we don't want to halt those processes because P1 is accessing this. So this is not a good idea at all. Okay, because by this I am putting everything on a halt other than the P1. So this is not a good idea. So what I got to do is I got to develop some kind of protocol. Okay, so that protocol makes it sure that it avoids the race condition. Okay, so in this case you're trying to schedule off, but everybody is everyone is, you know, is getting problem. Like I said, in India we have black money with few people, but demonetization has, you know, created problems for everyone. So we don't want to target everyone. Okay, we want to target the specific the process which is trying, those processes in contention actually, which are trying to access that critical resource, right? Like I said, the critical resource. Okay, so that means the critical resource is accessed using the critical section. The critical section is a piece of code which actually accesses that critical resource. So at that critical resource I may lock or unlock or do something else, and we have a lot of ways to do that in software, in hardware, and in many manners, in OS and programming languages. And this thing to avoid, so if two processes are accessing the and messing up, that's called a race condition. But if you are doing what, you are excluding the processes to mutually access a particular critical resource, then that's called in short mutex or mutual exclusion. Okay, now this mutual exclusion problem can be solved by many ways. So you can solve them using the software approach. We have two famous algorithms, Dekker's algorithm and Peterson's algorithm. We'll talk about them. Before that, we will see many we'll see 3-4 algorithms so that we have a good concept that what Dekker and Peterson is gonna do. Then we can have a hardware support where it's a test and set atomic operations. We'll talk about them later on. Then there is some operating system solutions like semaphores that we got to cover up in detail. Then program language solutions like monitors. Okay, like we got a Java where we can have a you know, in a programming language constructs which actually avoid mutual exclusion, and as well as we can avoid the deadlocks, which we'll talk about later on. In distributed operating systems we can have a message passing and so on. Okay, so this is actually the whole thing that we're gonna cover in our synchronization lectures. Okay, so this will take up many videos and we will talk them and all. So so this is all to have mutual exclusion or mutex. Okay, so whatever the solution you will take up, but you have to take care that they must, any solution must satisfy these three conditions. One is the mutual exclusion. Mutual exclusion is simple, that if you got a processes P1, P2, P3 and no two process can simultaneously access a critical resource, or in other words can simultaneously execute critical section. Critical section is a code which actually allows a process to have that critical resource or shared variable or something else. Okay, so mutual exclusion makes it sure that no two processes simultaneously do that. Okay, and the progress condition is that, say for example P1, P2, P3 are in contention to access this. Now there shouldn't be some other process which hamper you know, these contention processes from accessing the critical resource. Okay, I mean no other process can influence this decision. Okay, and bounded waiting means the decision to enter the critical section and to access the critical resource cannot be postponed indefinitely. There shouldn't be something that someone is hogging the resources quite often. Okay, and these guys are starving. It shouldn't be, the starvation shouldn't be there. there should be some kind of a justice with that. Okay, we'll try to have whether whatever the algorithm we'll choose, we'll try to gauge them as per these three criteria. So these three will become our criteria for any kind of mutual exclusion solution, right? So let's try to see here actually the Dekkers and Patterson algorithm. So we are talking about software approach. Okay, but before we can arrive to the Dekkers and Patterson's algorithm, we gotta discuss a few algorithms. By that, you will understand properly how Dekkers and Patterson's algorithm work and how they have arrived to that kind of algorithm. Okay, so with that we have a what's called as the first algorithm. So let's try to discuss now the first algorithm. Now this is our algorithm one, and it has a global variable, say turn. Okay, it has a global variable turn. Now it is a strict alternation. The guy who has a turn can access a critical section. Okay, and if you don't have your turn, you can't access a critical section. Say for example, let's go in a good way, for beginning, say let us put up in beginning turn to be 0. Now process 0, say for the process 0 comes up, and it is saying while turn not equal to 0. If it is not equal to 0, so it is untrue, because it's false, because turn is 0. So it will not do this thing. So it will skip this while excuse me, um, 1 second. So it will skip this whole while loop. This while loop is from here to here. So it will skip it, and it is going to do the critical section, and at the end it makes turn equals to 1. That means says, hey, it's the process 1's turn, and the process 1, say for example it was doing the critical section. For example, say whatever it is printing, or whatever it was doing, it takes some time, and in the meantime process 1 came. Okay, but it's saying while turn not equal to 1. This is true because turn is not 1, turn is 0 right now. So it's gonna wait forever here, right? So it's gonna wait till the process 0 makes turn 1. The moment it makes turn 1, it comes out of this while loop, busy wait or spin locking. It's spinning here. It was busy waiting here and wasting the CPU time, mind you. So it will come out of it and start doing the critical section and makes turn 0, and now turn is back to you guy. Okay, now first this seems to be a very simple algorithm, but and it seems that it has solved the critical section problem, mutual exclusion problem, that yeah, no, two processes can't execute simultaneously, because why? Because you don't have a turn, so you're gonna wait. Okay, so it's kind of simple law. But the thing is that, say for example, firstly the problem is that the process 0 should know about the process 1. That's why it's making turn 1. Okay, so this is the one problem. Second problem is what's called as a progress condition. The process 1 is not executing the critical section. It depends on the process 0. Now that is the progress condition, which tells us that it should not be, the decision to enter the critical section should not be made on the basis of some other process, because that process may be irrelevant. Now what does that mean? Say for example, here I'm saying that you are done. Okay, and you here, for example, process 0 comes in the beginning, turn is 0, so you did a critical section, you make turn 1. Now you can do your other job, no problem. And now process 1 comes in, turn is 1, he can do it. Okay, he can do the critical section, he doesn't wait because process turn is 1. Now at the end he makes turn 0. Say for example, the process 0 do not want to run critical section, but process 1 wants to run again the critical section. Say for example it was a printer, the process 1 want to print again, but the turn is 0, so it can't. When it comes back, it stays in this while loop forever, because process 0 never gonna make its turn 1. That's why we say progress condition, that if you want to access the critical section, the decision should not be made on the basis of some other process. Or for example, in this case, the process say turn was 0. You didn't run the while loop is false, so you run the critical section. You make turn 1. This guy comes in, okay, and the turn is 1. It can access the critical section, and it is kind of a dead. Maybe it dies in the critical section. This process is dead, or it has some deadlock. It's stuck there, or it crashes there, right? So it's killed. Now before it can make the turn 0, it's killed. So what will happen to the process 0? Now if process 0 wanna access the critical section, it can never ever access it, because it's waiting for some other process to make the turn 0. So we can this strict alteration, busy waiting, and progress condition is not met in this, so we say this algorithm can't work, so we got to do something else. So we move on to the algorithm second. So mind you, these algorithms are not the perfect solutions, but they will actually visualize, get you visualize, you get a clear view of what we gonna do in the Dekkers or Peterson's algorithm, right? So in algorithm second, what we do is we say that, hey, in algorithm 1 we are trying to set the turn of other guy. We say don't worry about the other guy, worry about yourself. So what we here have got two things, what's the two flags, okay, F1 and F2. And what we do is here is first, when the process comes, and say this is a kind of a complete code, zero code. So this is process P1 which begins, and it runs a while loop while true to begin. So that means this is the infinite while loop. So we say while F2, that means if flag F2 is, say for example, because I said there are two flags, F1 and F2, process 2 has an F2, process 1 has a flag F1. If F2 is true, what does that mean? That means F2 is accessing the critical section. And if F1 is true, that means P1 is accessing the critical section. So for process P1, because we are talking about process P1 here, if F2 is true, that means the process second is this time accessing critical section. So I should refrain. So what I'm gonna do is I keep testing. This is the spin lock. I keep testing whether the F2 is true or not. The moment the F2 becomes false, okay, that means other guy is not accessing the critical section. I make my flag true. That means my intentions that I want to access the critical section. Now the moment I set F1 true, that means I am locking it, so that if now a process second come, he may be chucking the F1. So the way the P1 accessing the F2, the P2 will be accessing the F1, right? So before I can access the critical section, I'm locking it. I'm saying F1 equals to true, so I'm putting a variable as a true here, okay? So it is like in a washroom, you got a variable here like a lock, okay? You make a lock true before entering the critical section, okay? But if it is already true, that means if somebody else is has locked it, so you're gonna test it in a spin loop, right? So same is here. So when you are done in a critical section, you can release the lock. You can say F1 equals to false. That means I am done. Now it can, other guy can do it. But I'm not saying I'm not using someone else's flag true or false. So I am minding my own business here, right? I'm only checking if somebody has locked it. I'm not gonna use it. But if I want to lock, I want to lock my own lock, okay? That is the process P1 has a F1 lock, and then it can release the lock here. It locks here. It releases the lock here, right? And so critical section between the lock and release lock. And then you can do your other processing. You end the while and you end the process P1. And process P2 has the same story to tell, that it will chuck the F1 here in a while loop. If F1 is true, that means process P1, say for example process P1 was doing critical section, it has made the F1 true. Now maybe P2 comes in, so it sees no, F1 is true, so I can't access the critical section because it is the P1, the process 1, which is accessing it right now. What I'm gonna do is we keep testing. I'm gonna wait, okay? And the moment F1 becomes false, like here in this line, I will come out of this loop and I will make my own flag true, and I'm gonna access the critical section, and then I make myself false because other guys maybe want to use it. So I release the lock, I lock it here, I lock it using this flag variable, then I do the critical section, I release the lock, and I do other processing later on. Okay, this seems to be kind of good. This is the parent process where we have the flags. Firstly, both the flags are false, whosoever comes, okay, and he can make its own flag as true and access the critical section. Okay, the other guy only checks if my flag is if others flag is true, I'm gonna wait. If then I will make my own flag true and access the critical section, and then release the lock by making my flag as false back, right? Now what is the problem in this algorithm? The problem is, now this was the good algorithm, this fixed the first algorithm's progress condition, but here there is a problem, a serious problem. That is, if process P1 and P2 came simultaneously, okay, when they came simultaneously in the beginning, both flags are false, right? Okay, now P1 checks here in its while loop that is F2, while F2 means while F2 is true, right? So it is false, right? And P2 sees while F1 that is F1 true, but it's false. So both these while loops will not run. So neither P1 nor P2 gonna wait. So what they will do is P1 will make its own flag true, P2 will make its own flag true here, and they both gonna access the critical section. The whole logic of mutex is failed here, right? So you can't do this. So this is a big drawback in this algorithm. If both the process comes in, because both of them test the other's flag, and that's going to be false in the beginning. Both of them think that nobody is here, it's only me, so both of them will make their flags true and start accessing critical section. So that's kind of a problem. So to fix it, we got to have a third algorithm. Now to remove the anomaly of the second algorithm, we say that do one thing, only one change, that is set your flag first to true and then test the other's flag. Because we were in second algorithm checking the other's flag, okay, that was coming false, and we were making our flag true. We say now no, do it one thing, make your flag true first, okay, make your intention clear that I want to access the critical section, then only then check the other guys. Okay, the rest of the code is same, but it will also have an anomaly. Say for example the process P1 comes in this scenario, take this scenario as an example. The process P1 comes in, okay, it sets its flag to be true, okay. Now maybe its time slice is over, okay, because process P1 is doing something that is here, and when it tries to access the critical section, only then we are doing this logic, right? Other than that, no. So process P1 got some time chunk, say in a time sharing machine or something, it got a round robin scheduling or whatever, so it gets its time slice, and it was trying to execute all these line of code, and it reached here, and it makes its flag true. The moment it makes the flag true, it timed up, okay. So it's preempted by the process P2. Now process P2 comes in, okay, it comes in here, and it makes its flag to be true. So it's making its flag true, okay, because we are making our flag true in the beginning. So it's making its flag true. Until then there's no problem. Now it goes to the while loop, while F1. What will happen here, because F1 is true, the process P1 has made its flag true, now it is preempted. Now process P2 has made its flag true. Now what will happen here is the process P2 will say while F1 is true, I'm gonna keep testing, because F1 is true, yes it is, I'm gonna keep testing. So I'm in a busy loop, and I'm waiting when F1 become false, and in the meantime my time slice is over. I'm preempting to this guy. Now this guy comes up, start running while F2 is true, and what will happen here is F2 is true, yes it is, so it will stay in busy looping, spin looping, in a spin lock here. It's spinning, and in the meantime its time is over, it goes to this guy and it's happening here. Its time is over, it goes to this guy, it's happening here, because it's waiting when the f1 becomes false, and it's waiting when f1 becomes false, and it's waiting when f2 becomes false. But nobody is actually progressing, so they are in a state of deadlock, right? This is the big problem with this algorithm, so we're gonna fix it somehow, right? So we do next is a fourth algorithm. Okay, now what will happen here is, why it's a deadlock, because we have an f1 true, and I'm seeing f2 is also true. That means that is a scenario when I have timed out and other guys also made its flag true, so that is a problem. So to avoid that, when both of the flags are true, I can use an if block, simple as it is. That is what we do in a fourth algorithm. Okay, I will use an if block here. So when I say if f1 is true, I may firstly, when I come in, the process p0 comes in, it makes its flag true, so it has a clear intention of accessing the critical section. Okay, and if it finds the f2 as well true, so it is a previous scenario, the f2 is also true, then what I do is I will release the lock. I will say f1 is false, I give other guy a chance. I am not so greedy. Okay, I'm not greedy, I'm saying no, let me give the chance to other guy. I make myself false. Okay, and if that is not so, if f2 is not there, I can access the critical section, no problem, and I can make my flag here, release the flag here. Okay, release the lock here, right? And same thing will be done by this guy, that if it makes first its flag true, then if it sees that if f1 is there, that means that f1 has come up, that means I will make my flag as false. Okay, it should be f2 equals to false, because I make my flag false. I don't want to make other guy false, because that is the progress condition, that will be problem. Okay, so this will check for the deadlock. So if both of the locks are there, I've released my lock, so that I'm giving chance to other guy. Okay, so this algorithm will never be in a deadlock. Say for example, if f1 has came to make it true and it timed out, okay, and then this guy comes in f2, it makes f2 as true. Okay, now both of the locks are true, but what will happen is he says if f1 is there, I gonna release the lock. I will not I've released lock. In the meantime, it released the lock, so it is not gonna it's not having a lock. So what will happen here is it goes back, say for example, if it times out, it goes back to this guy, and here in this guy, if f2 is there, which is not there because f2 has released its lock, it can access the critical section, no problem whatsoever, right? But what will happen in a scenario, we have one scenario where we can have an anomaly in it, that if both processes can differ, like for example, I say say consider this scenario, that I make myself true. Okay, and what I did is I say if f2, okay, I'm on here, I checked, I'm on this line, I have checked that f2 is there. Say for example, both of the guys are true, right? How both of the guys are true? That if like in a previous deadlock scenario, the both of the guys are true. Now they are coming back and forth. Now I'm on this line, for example, if f2, and I have seen it, yes, it is true, both of the f2 is true, so I concluded that f1 is true, f2 is true. So I want to run the this line of code in the if block where I've released the lock, but before doing that I'm timed out. Okay, so I have checked the condition that f2 is true, when both the locks are true, and before I can release the lock so that other guy can access this thing, I am timed out. So this line is to be done, so I'm here, right? So this line is to be done, I'm timed out, so I'm timed out to this guy, and this comes here. because if f2 is true, that means this line must have been done by the process p2. Now it checks here if f1 is there, because I have not released the lock. I timed out here in the process p1, timed out here, so I'm gonna go here, and I say yes. If f1, I'm saying yep, f1 is true, so I'm gonna release the lock. f2 is false, I'm making a release lock. So I'm not, when I release the lock, I'm not gonna go do critical section because I don't have a lock. So what I do is I will time out, I come here, and because I have now this time f2 is false, but that condition I can't check because I have checked it already. I'm on line this. Okay, so I will make my flag false. So in this scenario, f1 will make its flag false and f2 has made its flag false, so both of the flags are false, so nobody will enter the critical section, and this thing is called as a live lock. What do you call in Urdu, pehle aap. Okay, so pehle aap mein gaadi chali gayi means like I'm saying first you, he's saying first you, and in a first you and a first you, the train goes. So this is a problem here, right? Okay, so we have arrived few things. We have evolved our algorithms in that we are here now. Now we will use these 4 algorithms, okay, into our Peterson's algorithm and into our Decker algorithm, and that will be our next video. So hopefully this video is helpful. If it is not, that means you gotta watch it a couple more times maybe, and after that you can watch the next video on the Pearson's and Decker's algorithm, right? So this is the end of this segment. Until next time, ma salama.